The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Later on, I'll speak with Associate Professor Shohini Ghose about how quantum theory is being applied to communication security and protocols to great effect. But first, let's take a look at one of the biggest cracks of secure communication from World War II. Welcome to Science for the People. I'm Rochelle Saunders. When people think of World War II-era code breaking, we usually think of Alan Turing. His story is certainly most top of mind and well-known, especially with the recent release of the movie The Imitation Game. But his was not the only code-breaking success story to come out of Bletchley Park. William Thomas Tutte, known as Bill Tutte, also worked at Bletchley during World War II, breaking German ciphers and codes. With me is Professor Daniel Younger. He received his undergraduate and graduate degrees at Columbia University and went on to do a postdoctoral fellowship at Princeton. He joined the Faculty of Mathematics at the University of Waterloo in 1967, which was the inaugural year of that faculty. He became a full professor in 1975, up until his retirement in 2005. Since then, he has been an adjunct professor and professor emeritus. Dan, welcome to the show.
Well, thank you very much.
So who was Bill Tutte before he started at Bletchley Park?
Well, he grew up in England. Actually, he grew up in a horse town, the town which originally, even in the 1100s, raced horses. And to this day, the chief business is horse racing. And Bill himself was born in a horse stable, called Fitzroy House.
And what was he studying before being recruited at Bletchley Park?
When he grew up, he was a very good student and entered Cambridge University in Trinity College, and he was a student of chemistry there. Presumably that was for practical reasons. Actually, during the early part of the war, chemistry or the natural sciences were a reserved occupation, which would mean that he would not be subject to the draft. Mathematics in those days had a lesser reputation, and if he had majored in mathematics, he would have been subject to being drafted. However, I don't really know from him his reasons for choosing chemistry as his major.
So he started out in chemistry, but ultimately he would go on to choose mathematics. How did that happen?
Well, although he was studying chemistry and did achieve a first-class degree in that subject, he associated himself with three mathematical friends at Trinity who were majors in mathematics. And so the four of them worked together on a mathematical puzzle as undergraduates. And they had fun together doing this and had success. And this problem was trying to divide a square into smaller squares, each of the smaller squares being of a different size.
So do we know how Bill Tutte got recruited, especially given that he was doing chemistry at the time?
Yes, after his undergraduate degree, he continued on as a graduate student. And this would have been in the earliest years of the war, 1939 and 1940. However, he found himself really not enjoying his experience in doing chemistry experiments and said to his tutor that he would like to switch to mathematics, even knowing the incredible implication of that switch. And his tutor, Patrick Duff, knew more about such things, and he knew somehow about the fact that Bletchley was recruiting. And he sent Bill to an interview about which Bill did not understand the consequences. And in that interview, he was chosen to continue or at least to study in London the code-breaking problem, and eventually was chosen for Bletchley Park.
Do we know anything about what the qualifications were that Bletchley Park recruiters were looking for? I mean, what did they see in Bill Tutte that they thought might make him an excellent codebreaker?
Well, Bill thinks that it was that he had done this work of breaking, analyzing with his mathematical friends, this puzzle of breaking a square into smaller squares, which was a highly mathematical problem, and this needed a very mathematical solution. So I think they saw in him someone who was particularly adept at solving puzzles.
And code breaking is definitely, if not anything else, a very difficult puzzle.
A huge puzzle, yes. That's exactly what I think they saw in Bill.
So at what point did Bill realize what he was being recruited for?
Oh, well, I think that when he went to cryptographic school in London, why he knew that it was being recruited for possible work in cryptography. However, exactly what role he would play and the fact that he would later come to play a major role was not, of course, known to him at that time.
So at Bletchley Park, what was Bill's first project?
When he was recruited, he must have done very well in the studies in London, because he was recruited for the research section, which had been just set up at that time, which would have been in May 1941. And the research section was the study of codes which had not yet been broken. When he got there, the research section was concerned with an Italian cipher that was used by the Italian Navy it used the Hagelin machine, a machine of Swedish manufacture, a machine which was known to Bletchleyites because it was a machine which was commercially available.
And what was, I guess, they needed to crack the code that this machine created?
Exactly. And so they did that within a few months, because this was not a high-level code. It was just supposed to provide temporary security. And so they were able to study this and within a few months decipher or decrypt how to break messages or how to decipher messages using this machine.
And so that project was, I guess, probably a good starter project. It sounded like it was broken reasonably quickly.
Oh, that's right. Within several months. I don't know how long they had been working on it before Bill got there, but probably not very long. The whole project was dealt with in about several months and then became part of some part of Bletchley that was concerned with the breaking of traffic rather than how to do it.
You're listening to Science for the People, and today we're talking about Bill Tutte, a Bletchley Park codebreaker during World War II, with his colleague and friend, Professor Dan Younger. So after the Italian cipher, what was Bill Tutte's next project at Bletchley?
At that time, and a little bit before, Bill was introduced to the machine called tunny. That was the British word for tuna fish, and they used that because they were just trying to find some name that was convenient for them. They didn't know what machine actually produced this. They started getting messages which were of a very high-speed character that were produced by a teletype machine. And at first they didn't even know what the nature of these signals are. It was just sort of a moan or a high whir that they heard. But eventually, by recording these and analyzing them, they understood that it was, in fact, produced by a teletype machine.
So these transmissions that they received were an audible transmission that were produced by a teletype machine?
They were received by radio.
Okay.
They had set up over the east side of England large radio towers which would intercept rather sensitively messages that were sent anywhere in Europe.
So who was using this particular code?
Well, this particular code, I suppose they didn't understand at first, but was used at a high level by between the high command of the army and Hitler himself in Berlin and near Berlin to the various generals who were in the field, either in Russia or in the Middle East or in Italy. So these were used at a very high level, and they were generally strategic type messages. So these were very important messages.
They sound like they held really valuable information.
That's right, and in fact they had built a very special machine to make sure that no one would be able to break these messages. One very important thing was that the research section was set up soon after they first heard these signals. And so in the initial setting up, they were also in the process of beginning to try to understand how these messages were made up.
And so just to be clear for our listeners, this tunny, is that the pronunciation correct? Tunny or tunny? Tunny?
Tunny. But in North American terminology, it would be tuna fish.
Okay. So this tunny code, it has nothing to do with the Enigma code that obviously has been popularized and a lot of people know about.
That's absolutely true. The The Enigma machine was a different type of machine which was often located, shall we say, in a submarine or in some place that was no larger than a typewriter. The machines, the Tunny machine, which turned out to be made by Lorenz, so sometimes it's easier to say the Lorenz machine, was a rather large, heavy, 3-foot cubic machine which was attached to a teletype, which wouldn't be suitable for any kind of work in the field. It was mainly for headquarters.
So these are ciphers that are used for really high-level, high-strategic, high-value messages for the German military. How did these machines work?
Well, they take the message that comes off a teletype and add another message of the same type to send a message over a radio link, which has the same character as a teletype message, except that it's been obfuscated by this addition of two messages. The added message is called the key, the part that's being produced by the machine.
So it's essentially taking other messages, putting them into the important message and sort of mixing things around so it's hard to tell what the real message is.
Yes, and this key, this added message, was gotten by using 12 different rotors and whirling them around, and they had different sizes and different interactions so as to make a very confusing pattern.
So it sounds like Bill Tutte had quite a challenge ahead of him. What did the team at Bletchley have to work with to try and crack this cipher?
Well, one of the important things in sending such messages was that one should always change the setting of the machine, the setting of the enciphering machine, every time one sends a new message. And so in a particular case, why they forgot to do this, and they sent the same message twice. And now sending the same message twice with the same encoding should produce the same effect, which, if it did, wouldn't be at all helpful. But since they were sending it again, well, they put in maybe an extra space at the end of a sentence, or they said didn't instead of did not. And so they actually were coding a slightly different message. And sending two slightly different messages on the same setting is a very grave fault, called the depth by Bletchleyites. And the depth was usable to figure out what the added message was. And so by the time Bill came along, they'd had a key, a section of key, that is the part that's actually added, of 4,000 letters, which they didn't know what to do with. And he was a young man, had just finished his other work, and they said, well, can you see what to do with this 4,000 letter section of key? And so he was presented with it. And several weeks later, not longer than that, maybe a month or so, why he came up with this idea, or he slowly began to figure out not what the message was, but what the actual structure of the machine that produced this. He first figured out that it had 12 wheels, and he then figured out that the first wheel had 41 spokes, and the second wheel had 43 spokes. All of this information gained from this one section of tape.
Wow, that's amazing that somebody can look at what I'm assuming to most of us would appear to be gibberish and be able to figure out the physical dimension, or not dimensions, but the physical machine to some extent. That's fascinating.
Absolutely. After that was done, it was as if they'd had an actual machine there in their laboratory. They didn't really need a machine. They didn't need somebody to capture a machine or anything like that, because they effectively had one sitting in front of them.
So I'm assuming that wasn't the end of the story, because things are never quite that easy. They did run into problems with Tunny later on as well.
Yes, but first I want to emphasize that this must have caused a tremendous buzz around there, because Bill Tutte was given a fellowship at Trinity College for this initial accomplishment. However, once you know what a machine is, it still doesn't enable you to cipher messages which this machine processes. So, you now just know what the machine is. You now just know what was known by Bletchley already when they had the Hagelin machine, because they knew what the Hagelin machine was. It was what the workers knew when they had the Enigma machine, because the Enigma machine was known. But here now they at least knew what the machine was, but knowing what the machine was still left the incredible problem of trying to find out how to break messages using that machine.
This is Science for the People, and I'll be right back with University of Waterloo mathematician Professor Dan Younger to learn more about the World War II codebreaker and mathematician William Tutte after this.
Science for the People is a weekly radio show exploring everyday life from a scientific perspective. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to connect with us on Facebook, Twitter, and Google+, or to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back to Science for the People. I'm Rochelle Saunders. With me is Professor Dan Younger, a colleague and friend of Bill Tutte, a Bletchley Park mathematician who broke the World War II Lorenz cipher. Okay, so they understand to some extent how the machine works, or what it sort of looks like at a fairly high level. What's the next step for Bill Tutte?
For a while, they depended on mistakes which were made in the use of the machine, the sending of two messages with using the same key. And they also depended somewhat on the fact that the setting of the machine was put as the first 12 letters in sending a message. But eventually they stopped. They realized that that wasn't a good thing to do. And so they cleared up, they fixed that particular flaw in their way of using the machine. And then they were left with what Bill Tutte in the winter of 43 called their winter of discontent, when they could no longer decipher messages that were produced by the Tunny machine. But it was then that Tutte came up with the method for breaking messages by Tunny.
So what was that method? I believe this is the statistical method?
Absolutely, yes. The statistical method takes advantage of the characteristics of the code that's used for encoding messages by teletype. When a message in teletype, when they set up the code, they made it so that common letters, such as E, would have less holes in the tape than obscure letters like Q. And because of that, a machine can, if they compare messages, that can determine whether it's more likely that a message is actually a true message or one which is not a valid message, based on whether it uses fewer holes than if it was interpreted another way. And this statistical idea was what was the basis of Tutte's procedure. However, he actually was able to say that even in a more particular way, one could do this hole by hole rather than overall. Nevertheless, there still requires thousands of choices in order to determine which one is correct. And these thousands of choices have to be done very quickly. So it left him the problem, yes, here's a method for breaking codes that are produced by this machine. But this method could only be realized if you have an electronic computer. Well, they didn't have an electronic computer. But there was a person there at Bletchley who had been thinking that they would need an electronic computer. And he was a person who worked for the British Postal Service, the service that was concerned with the telephone service in England at that time. And he was therefore using and thinking that electronic methods would be necessary. And so he and his co-workers developed an electronic computer that actually realizes Tutte's statistical method for breaking codes.
So is this machine the Colossus?
It is. It was a machine giant by those standards, and still giant today, which was named by the British Colossus.
Now, Colossus I have read a little bit about, and I understand that Colossus has a lot of vacuum tubes built into it. I've heard it's a very mechanical machine. Of course, we think of computers today as kind of boxes where all of the mechanics is hidden away from us, but based on pictures of Colossus, it was a very, like you could see the bits moving around, which seems like it would be very different from what we call a computer today.
Well, I think I would not like to emphasize the distinctions because the vacuum tubes were electronic. That is, it wasn't based on a mechanical turning. The machine which was used to break the Enigma did involve electromechanical parts. But the important thing is that essentially vacuum tubes were and are equivalent to transistors. And so all of this is done in a way that you characterize as in a hidden way because it's all just based on the passing of electrons.
So was Colossus built specifically to be able to help them break the Lorenz cipher, or was it built more generally and then sort of applied for or programmed to be able to deal with the Lorenz cipher?
The parts of it were built really for electronic switching relative to the telephone service. However, in the way in which they configured it, it was specifically built to realize Bill Tutte's statistical method.
So Bill Tutte's work allowed it to be possible for a machine to actually make it through all of the potential combinations. Is that a pretty good understanding?
That was a very well said statement. Yes, that's exactly what it does.
So what happened to Colossus after the war?
Well, they wanted to hide the methods that had been used to break codes, and so Churchill, at the end of the war, said that all Colossus machines should be destroyed and that the plans should be thrown away and that no reference or mention of this should ever be made. The idea was that they did not want to tell how such a sophisticated breaking of codes was done.
How valuable was it to the British that we could break the German codes, this high-level strategic code at this time?
It was, in the latter part of the war, absolutely significant, and particularly one characterized it, or one states it, that it was important at D-Day and all of the events of the war after that. And it was important because one could tell what the generals were saying to each other and what the high command in Berlin was saying to the generals. So they knew exactly whether or not the decision to land their forces in a particular place was understood or whether the Germans were thinking that it would land in a place that they'd sort of publicized might be a landing place. So they were actually able to make good decisions, strategic decisions, based on their understanding from the decrypts from Tutte.
So obviously all of this work at Bletchley during World War II was kept secret. You talked a little bit about how Colossus was actually destroyed. So after the war, what did Bill Tutte do, and where did he go?
Well, after the war, Bill Tutte, having signed the Official Secrets Act saying that he would never, as a matter of security, ever say what he did during the war, he went back to Trinity College, where he was now in the extraordinary position of being both a fellow of Trinity and a graduate student of Trinity, and he studied mathematics. He got his PhD in mathematics.
What type of mathematics did Bill Tutte specialize in?
He studied the same broad type of mathematics that's necessary in code breaking, that is combinatorial mathematics. And this was also the type of mathematics that he and his friends had used in analyzing the problem of breaking a square into smaller squares. This was not a very popular form of mathematics in that time, and he was advised that he should do something more useful, such as differential equations. But he, now having had the prestige of being a fellow, was able to decide for himself what he should do. And so he chose to continue on in combinatorial mathematics.
And I'm sure the irony of having just used that very skill set to help win the war was not lost on him at that time of that advice either.
Well, that's of course, yes, exactly. Well said.
So Now, Bill Tutte actually ended up in Canada, which is an interesting part of the story and how I first Bill Tutte was brought to my attention. So how did he end up first at the U of T in Toronto and then later on at the University of Waterloo?
Well, as I say, his advisor in mathematics after the war advised him to take a different form of mathematics, such as differential equations, because I think he understood that it was not likely that he would get a position based on his work in combinatorial mathematics. However, after the war, that turned out to be the case. And however, there was a person that he did know who was at Trinity earlier, a very famous geometer, Donald Coxeter, who did know of that work and himself did something not like that, but close to that, namely geometry. And he applied through Donald Coxeter for a position at the University of Toronto and was accepted. So he moved to Toronto. Actually, it was, I think, very fortunate in many ways to move to a new continent, because there, since he was under this vow of secrecy, it was very unlikely that people would question him as to, well, what were you doing during the war?
So throughout most of his life following the war, obviously Bill Tutte had to keep his work at Bletchley secret. When was his work declassified in such a way that he was able to be more forthcoming about his experiences during World War II?
Well, the Enigma machine and what happened to it was, well, it too was supposed to be a secret, but somehow or other, why it came out during the 1970s. And but the secret relative to the Tutte or Lorenz machine continued on, and actually Bill was almost 80 when people started writing and talking about it. So when others wrote, and in particular there was, on his 80th birthday, a publication which described what was done, and since that was in the New Scientist, a magazine that was distributed internationally, why then, since other people were talking about it, Bill felt that the vow of secrecy was in effect broken. Maybe I should emphasize another point, that a person who was part of the Secret Service, Tony Sale, he was disturbed by the fact that this British accomplishment, namely this early electronic computer, was not part of the understanding of computer scientists as being the first electronic computer. And he asked the government because he knew about this project, he asked the government if they would allow him to reconstruct a Colossus machine. And at first they were reluctant to do that for all of these reasons, but eventually they did say, okay, you can reconstruct a Colossus machine. Well, once you allow someone to reconstruct the Colossus machine, why then you're in the position that you almost are forced to say what that machine was used for. And I think Tony Sale, who wanted the machine to be built, also understood that you would then have to say what the machine was used for.
So what did Bill Tutte make of his own work and his legacy?
Well, I mean, one of the important points is that he went on to become one of the most important combinatorial mathematicians of our era. He had a very successful career, independent of whatever happened during the war. However, it was very important for him to finally be able to tell that part of his life story.
Do you think without his work during World War II at Bletchley Park that he would have ultimately chosen to go into combinatorics and mathematics?
Well, of course, it's hard to understand a person's career choices, but I think it is true that he was already headed in that direction based on his undergraduate work with his three friends.
Dan, thanks so much for being here and sharing Bill's story with us. He's a really fascinating story and an interesting man.
I agree. A wonderful person.
If you would like to learn more about Bill Tutte, we've got some links to get you started on our website at scienceforthepeople.ca. When we come back, we'll be stepping forward in time, looking at how we're starting to apply quantum theory to communication security problems with Associate Professor and Theoretical Physicist Shohini Ghose. Stay tuned.
Science for the People is a weekly radio show exploring everyday life from a scientific perspective. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to connect with us on Facebook, Twitter, and Google+, or to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back to Science for the People. With me is Shohini Ghose, an associate professor of physics and computer science and director of the Center for Women in Science at Wilfrid Laurier University in Waterloo, Canada. She's a theoretical physicist who examines how the laws of quantum physics might be harnessed to transform computation and communication. Her research and teaching has earned her numerous awards, including a Women of Waterloo Education Award and a prestigious TED Fellowship. She's an affiliate of the Perimeter Institute for Theoretical Physics and the Institute for Quantum Computing at the University of Waterloo. Shohini, welcome to the show.
Thanks very much.
Okay, we wanted to talk about quantum security, but I think we need to back up a little bit and talk a bit about the quantum computer. So can you walk us through kind of what that is and how it might work?
Sure. So, let's start first with our computers today and how they work. And basically what they do is they take all information and encode it in binary digits, zeros and ones essentially. And then our computers, our laptops, all of the transistors in our laptops are switches that can turn on and off current, so that when the switch is on, you have a 1, and when it's off, maybe you have a 0. And all that we're doing is manipulating the zeros and ones in certain ways to perform different kinds of tasks. So in fact, what we should actually realize is that that quantum physics is already part of our current computers. Because in order to build these amazing transistors, billions of them that are actually working inside our current computers, we had to actually understand the structure of atoms and how atoms interact with light and how to control lasers and things like this. So all of that is already built into our current computers. But the next generation, when we talk quantum computers, we're talking about using this other layer of quantum physics that we haven't used as yet. And this is moving away from this idea of just manipulating zeros and ones and switching them on and off. And the idea there is to use this other part of quantum physics, which is basically about uncertainty and probability. So in quantum physics, probability is actually a very, very important part of the theory itself. So instead of having the situation where you have a bit which is either 0 or 1, we can have a quantum bit which has a likelihood, a probability that it is 0 and a probability that it is 1. And it may seem a little weird and may seem, how can we possibly use this for doing precise computing, because we have more uncertainty. But turns out it actually has some power, because instead we can flip it around and say, wait, well, it has some likelihood of 0 and a likelihood of 1. So if I want to do a calculation using 0 and another calculation using 1, I could do both, because there's some chance that I have the 0 calculation and some chance I have the 1 calculation. So on a large scale, it seems like we can be massively parallelized because of this idea of combining zeros and ones and not just either 0 or 1. But there's, of course, a subtlety there. That is, when we finally want a final answer to be output, we will have to measure our entire quantum system, and then we'll get either the 0 answer or the 1 answer. So basically what quantum computing is all about is to design clever algorithms where when we finally do our final measurement and get the answer, it is the correct answer, instead of just getting randomly the 0 answer or the 1 answer. So really, this is the heart of quantum computing. How can we use this feature of uncertainty and probabilities in quantum physics to improve and utilize all the parallel potential in there to do improved quantum computing, as well as maybe tasks that we can't even do so far with our current classical computers.
So can you give us an example of a task that a current computer would have a lot of trouble with that a quantum computer might be able to do with relative ease?
Yes. So I think the one that's specifically very important when we talk about security is a factoring of numbers. So for example, if I ask you, what are the factors of the number 15? That's pretty easy. You'll probably say, hey, 3 and 5. But, if I say, what about a number like 143? That's not that big of a number, but it probably might take you some time to figure out what the factors are. And when we go to numbers that have 200 or 300 digits, turns out this is a really hard problem to do. In fact, I think the record now is something around 230 or 240 digit numbers, and we would need massive computing power to be able to factorize numbers larger than that. So that's a problem that our current computers have real trouble with. But on a quantum computer, we actually know of an algorithm that was developed in the 90s by a scientist named Peter Shor, which is a quantum-based algorithm, which uses this idea of probabilities and uncertainties and utilizes it in this really clever way to be able to actually factor these large numbers very quickly. So, yeah.
Wow. So just so that our listeners understand, are there any actual working quantum computers out there today?
So there's been definitely a lot of progress on the experimental side in implementing specific algorithms, such as this factoring algorithm. So different experimental groups around the world have been building these sort of lab quantum computers, if you like, on a small scale to demonstrate that these algorithms actually work and work faster than what you would expect any classical computer to be able to do. And so, for example, the factoring algorithm has been demonstrated up to, I believe, the recently it was done for the number 21, which doesn't seem like a really big improvement or a big deal to be able to factor the number 21, but it's really a proof of principle. On the large scale, at the commercial level, we don't really have a full-scale quantum computer. There are companies out there who are developing very specific kinds of devices. One of these companies that you may have heard of in the news a lot is D-Wave, which is looking at solving certain kinds of search problems using a quantum device. It's not clear yet whether they've actually done anything that demonstrates a quantum speed up, but there are companies, in fact, who are investing in this, and some of the large companies, computer companies like HPE, IBM, many are actually now focusing on having a quantum computing research group. So this is an ongoing kind of area of research and development.
So an ongoing source of research, but not necessarily something you can buy at Future Shop just yet.
Not quite yet.
So the idea of quantum computing actually created a big problem for computer-based security, didn't it?
That's right. So this brings me back to this question of factoring. The reason this is a really important and interesting problem is not just because it's hard, but hard problems are, in fact, at the heart of security. So, for example, if you want to, log into your bank account on the internet, you have to, of course, enter your password, but you want to make sure that nobody else can, see your password. So basically you have to send that data in some kind of encrypted form. And the standard encryption protocol that is used around the world today is something called RSA encryption. And that encryption basically relies on this idea that there's some secret key that only you and the bank have, and that key is basically the factors of some very large prime number, a very large number, the prime factors of a very large number. And so if anybody else wants to actually find that key, they would have to, the only access they have is this large number, and they would have to, in fact, figure out what those prime factors are in order to be able to break into your bank account. So this is what makes this problem, specifically factoring, a very important problem. So as soon as as Shor's algorithm was developed, people started realizing, oh wait, now if this algorithm is actually implemented on a quantum computer, it could break all the current encryption protocols we have in minutes. So this, of course, causes all kinds of issues around security for not just us personally with all of our information, but of course governments and organizations around the world who rely on privacy.
So how well, I guess our current standards probably wouldn't work very well in an era of quantum computing, like you say. It sounds like it would be very easy to crack something. Mm-hmm.
Well, easy in the sense that once we have a working quantum computer, the latest encryption standards use numbers, these large numbers that have maybe two prime numbers that they are that you multiply together to get this large number. Well, the large number itself has maybe, I believe we're talking about 1,000 to 2,000 bit number in binary digits. And those, a 2,000 bit number turns out to be much larger than the current record for the size of a number that has been factorized. So using classical computers, these kinds of encryptions seem to be pretty safe for now. But a quantum computer, as I said, with about, a few thousand bit computer, which is really, small relative to the size of the number of bits used in our current regular classical computers, that kind of a quantum computer would be able to crack these codes in minutes. However, we are not there yet in terms of actually practically building such a computer. There are many efforts around the world, but turns out quantum information is very fragile. So it's very difficult to be able to control the actual algorithm implementation on a quantum computer. And although we know the algorithm, it's hard to control it. So it's an engineering task. And but once we maybe have a breakthrough where we can actually control these tasks and implement them well, then yes, we do have a big problem.
Okay, so this is not something that necessarily the average person on the street needs to worry about right now. Our credit card information is currently, safe. Let's say safe.
Yes, so nothing to worry about right now.
But we certainly don't want to wait to deal with this problem until the point when quantum computing becomes a real thing. So there has actually already been a lot of steps taken to create security protocols that work within a quantum computing environment.
That's right. So interestingly, on one hand, quantum computers can break our current encryption standards, but the solution may also be offered through quantum mechanics. So as I was saying, quantum theory has at its heart this idea of uncertainty and probabilities and such. And you've probably heard of this well-known principle called the Heisenberg uncertainty principle, which basically says that at the quantum level, there are certain properties of a system that cannot be known precisely at the same time. So, for example, let's say you have a GPS and you use it, you can see where you are located on the planet, and you can also tell how fast you're going. Let's say you're in your car, it'll tell you which direction you're going, how fast you're going. Well, all that information, although at the classical level, seems like we have all that information, there is some level of precision to how well we can know these kinds of information. So in fact, at the quantum level, when we talk about the location and the motion of an electron or an atom, turns out you cannot precisely know both its position and its momentum, which is how fast it's going and where it's going. You cannot know both of these kinds of properties exactly at the same time. And there are other such sets of properties. For example, if you have light, light has a property called polarization. And I'm sure you've heard of polarized glasses, which actually, in fact, use exactly this property of light to block the polarization in a particular direction, which means there's less light that enters your eyes. So those are the polarized sunglasses. So polarization is actually something that when we have sunlight, we have polarization in many different directions. But if you can take polarization and prepare it so that it is only, let's say, in the horizontal direction, then if somebody is trying to observe that light, then they would need an analyzer which is aligned along that vertical direction as well to be able to see the light and observe it. So polarization is a way where we can actually use this uncertainty that is built into quantum physics. Because if you know the polarization in, let's say, the horizontal and vertical direction, you actually lose the precision of knowing the polarization in some other directions, for example, along the 45-degree axis or the minus 45-degree axis. So the idea behind this is to try to generate a secret key between two parties who want to communicate, Alice and Bob, which is not known to anybody else. So Alice and Bob are trying to generate a key that nobody else can know. And what they do is Alice will randomly pick a polarization direction and prepare her photon, which is a packet of light, along that polarization direction and send it off to Bob. And she'll do this for many such photons. On Bob's side, he will randomly pick a direction along which to observe the polarization. And they both have their choice of picking randomly from one of two different polarization directions, two sets of polarization direction. And so if their polarization directions actually randomly agree, then they will both know the correct direction of polarization. So Bob will be able to accurately measure Alice's sent photon, the polarization of Alice's photon, if he by random chance happens to pick the same direction to measure the polarization. However, if he happens to randomly pick the wrong direction, he's not going to get the correct polarization that Alice has sent. So at the end of this whole protocol, after many, many photons have been sent, Alice and Bob compare what were their choices for the polarization directions, not the actual polarization that was actually sent, just what directions that they picked. So they throw away all of the outcomes where their polarization direction randomly disagreed and only keep the outcomes where their polarizations agreed. And in this way, they know that they have both got the same polarization and they've observed the same polarization. What Alice sends is what Bob receives. So they've created a key. For example, if I call horizontal being 0 and vertical being 1, or plus 45 degrees being 0 and minus 45 degrees being 1, no matter what the choices were, Alice and Bob will agree on their string of zeros and ones. So they have both on each side generated a common string. However, if there's somebody who's listening in or trying to steal the string, they would not have known ahead of time either how to observe, what direction to observe the polarization in. So they would not necessarily be able to have the correct outcomes as well.
This is really I find one of the more fascinating parts of some quantum security ideas is, throughout history, sending codes back and forth or keys in order to read codes, there's always been this element of risk. You don't know who's eavesdropping. You don't know if they've got the data or not. Yeah. But what's really kind of cool about these quantum security protocols is we would actually, in these cases, know if someone had intercepted the message.
That's exactly right. There is no way for an eavesdropper to actually listen in to the message without leaving some trace. That's another amazing property of this whole uncertainty business. So anytime an eavesdropper tries to listen in, it will disturb the actual signal that's being sent from Alice to Bob. So that can be detected. There are protocols by which Alice and Bob will compare their parts of the key and know if there has been an eavesdropper or not. So there is no way to be completely secret. And that's really why this is a provably secure way of generating keys. Because even if Eve, the eavesdropper, had a quantum computer, she would still not be able to hide herself perfectly from Alice and Bob.
So she could read the message, but she wouldn't be able to hide the fact that she read the message, basically.
Yeah, basically she could. For example, she could intercept the message and steal it and then try to replace it, right? She could read the message and then she could try to replace it so that she's trying to fool Bob into thinking that her replaced message is the correct message. But actually Alice and Bob can do some communication and can figure out that she has replaced the message.
Okay, so yeah. Is this just a theory right now, a hypothetical, or are there real practical applications of this working in the world right now?
No, in fact, this quantum key distribution protocol is one of the most advanced of the new generation of quantum technologies that people are working on. There are, again, companies out there that are actually building quantum devices, commercial key distribution devices. I believe there's an American company. There's also a company in Europe, based in Geneva, I believe, that are actually producing these devices. And as I said, the standard implementation of this is with lasers and light pulses. And that's a pretty well-established technology already, which is why this particular protocol is pretty well advanced. There are actually quantum communication networks that have been set up in different parts of the world. There's a network in Boston where quantum key distribution is used to ensure security in the network. In the Geneva area, there's also a network. And in fact, I believe in one of the local elections in Switzerland, the quantum key distribution technique was used to try to ensure security in the voting process itself. And that was used mostly as a way to prove that this protocol works. That being said, I do want to mention, though, that the practical devices that are being sold, we have to be really careful to make sure that they really are as secure as they claim to be. Because quantum key distribution, as I said, is literally unconditionally secure, meaning no matter what computer or eavesdropping device you may have, regardless of how good it is, you should not be able to break the key. No, given the current known laws of physics, there is no device out there. We can prove that you cannot build a device to break this. However, current technology has, of course, errors and flaws. And there's, in fact, a research group whose research goal is to try to hack into existing current practical devices. And they have been, in fact, able to hack into most of the devices that are actually commercially available. And that is basically not based on violating some laws of physics, but by showing that there's certain vulnerabilities in the practical system in terms of how good are the photon detectors, how good is your channel itself, and things like this. So there's still room for improvement in that area.
So you mentioned lasers, and that strikes me as something that probably the average person on the street wouldn't be able to get a hold of. So I'm assuming these devices, the ones that are currently available, are probably pretty expensive?
I'd say so, yeah.
And what about difficulty level? Are they difficult to learn how to use? Is this something that you kind of have to be trained in quantum physics and really understand it? Or is it something that, I'm thinking a business user working at IBM would be able to do?
No. So, as I said, this is not stuff you can buy off the shelf as yet. And certainly I'm sure they are very, very expensive. Their client lists, the company's client lists probably include, governments and banks and, major organizations. But that being said, the quantum part of the protocol should really be a black box for the user. So apart from the actual quantum key distribution part, which requires, generating these polarization states of light and sending them and making sure that the photon detectors on the other side work well, those parts are all part of a black box, which basically it's sort of like, when you buy a laptop or you buy a Blu-ray player, you don't have to know how the actual Blu-ray laser works inside a Blu-ray player to be able to use the player. So similarly, these devices for the commercial market, they are being designed in such a way that when you buy the device, of course, there's some kind of instruction manual, but it's not at the level where you actually have to know the quantum physics to be able to operate the device. Otherwise, you're right. It's not going to be very easy to operate it. Now, obviously, if the device fails and you have to fix it, you may want to know some quantum physics, but most likely you'll send it back to the company.
So if I asked you to just speculate for a second, your best guess, when would something like this be available to the more, let's say, mass market consumer?
Well, as I said, in principle, if your small business can afford it, these companies are on the internet. You can look up their websites. I believe the one in the Boston, New York area is called Magic. And you can go to their websites and they try to explain how their device works. And if you contact them, they can give you a price list. And in principle, you can buy them. But as I said, they might not be too affordable right now. So, but the technology keeps getting better. So like every other technology, prices will decrease over time. But this is the kind of security protocol that you want, major organizations to implement, like the bank, so that you on your side, you don't have to necessarily do much. You want to get to a point where you sort of log in and you're not even seeing that there's a quantum key distribution that's happening, which is ensuring the safety of your password. That should all happen in the background. Maybe you'll be asked to, have some off-the-shelf device that you plug into your current laptop. Maybe that will be how it will be distributed. But all of the sort of heavy lifting in terms of setting up the network and having the quantum protocols, that are ensuring the security. That's stuff that I guess when you turn on your laptop or when you're using some device on some open network, you shouldn't necessarily see all that as a user, apart from buying maybe a device that maybe you plug into your computer.
I do hope that one day I might be able to say that my iPhone is legitimately quantum inside. That would be very exciting for me.
It already is, thanks to all of the transistors in there anyway. That's what I call my device, a quantum device.
So just to end, you mentioned that there's still some engineering things to work out and that people are trying to hack into to some of the actual engineering of the devices. Mm-hmm. But what are some of the other research questions or challenges that we're still working on with this research?
So I think we're kind of just scratching the surface when it comes to exploiting all these weird properties of quantum physics. One of the things that I myself and many other researchers around the world are looking at is to try to see how else can we harness the laws of quantum physics for communication in large-scale networks. So far I've sort of talked about when, one person, Alice, is trying to send a message to another person, Bob, or when you are as an individual logging into your specific bank account. But what if we have a group of people who are trying to communicate, or maybe in the group somebody wants to communicate privately with, two other people in the group, or maybe you want to make a statement or tell everybody something, but you don't want people to know who you are. So anonymity is another aspect here. Privacy and security comes up in all kinds of large-scale applications, for example, like in voting. And we all know what a huge, issue that is. Ensuring, privacy and complete security of the ballot is a real major challenge. So these are some of the questions that I think quantum physics may have an answer to, and all kinds of interesting new ways of approaching security and privacy may be possible, especially in these large-scale communication networks. So that's on the sort of theory side, and that's part of what I myself as a theoretical physicist work on. But the other aspect is on the applied side, which is this: how do you actually build a quantum computer and scale it up so it's a large-scale computer that will actually be functional, even if it's not something that we all have in our homes as an individual device. Can we even build a large-scale computer that will be stable enough and robust enough to implement something like the factoring algorithm? That's something that is a huge area of research today around the world, and progress is being made. But as I said, quantum information is fragile, and one of the great challenges is how do you correct errors that happen in these kinds of algorithms? And that's a big focus of research. Once we solve that issue, I think scalability will follow.
I do actually have one last question. So quantum physics, once you get talking about it to, I think, the average person, this is one of the ones that if their eyes are going to glaze over, quite often it does start glazing over, which I'm certain you've experienced. Do you think an increase in applications for the more difficult parts of quantum physics, the ones that are trickier for people to grasp, might result in an uptick of interest and a less glazed look from people?
That's a really good question. I haven't thought of that as an actual benefit of applications of quantum physics, in fact. But it's a good way of looking at it. Maybe that's true. People will be more interested if they know it benefits them personally. But I have to say, I get, both kinds of reactions. Certainly a lot of people may feel, oh my gosh, what is this? This is all very strange. But as I tell my own students when I'm teaching this stuff in class, when you don't get quantum physics, you're getting it. So I think you get a lot of interest too from people, because the point is that yes, quantum physics can't be explained using our current language and laws of classical physics. That's the whole point. If we could explain it easily, then it wouldn't be that interesting. But we cannot. Even our language is not good enough because it's so counterintuitive, the theory itself. So that is the whole interesting and exciting part of quantum physics. So that's sort of the kind of message that I like to put out there, that in quantum physics, weird is actually a good word.
Shohini, thanks so much for being here and joining us again. It's great to have you.
Thank you.
If you want to learn more about Shohini Ghose or her work, we will have links to get you started in the show notes for today's episode at our website, scienceforthepeople.ca. There you can download all our past episodes and explore our entire back catalog. While you're visiting and clicking links, you can also click over to our Twitter feed, our Facebook page, or our profile on iTunes, where you can subscribe to have new episodes of the show downloaded to your devices while you're sleeping. Thanks for listening, and we'll see you next time on Science for the People.
Science for the People is recorded in Edmonton, Alberta. The show is produced by Rochelle Saunders. Ryan Bromsgrove is our promotions manager. Our social media manager is Chelsea Butler. K.O. Myers updates our website. Helen Quivalon is our publishing liaison. Ed Haynes is our guest coordinator. We get research help from Josh Witten. The show is edited by K.O. Myers and Ryan Bromsgrove. Our theme song was written and recorded by Fractal Pattern, and its title is Binary Consequence. The show is hosted by Rochelle Saunders, Marie Claire Shanahan, and me, Desiree Schell.